Now on Monday, we tried to apply Gauss' law to drive the electric field. But you can also use the Gauss' law to calculate the charge if you know the electric field. So let's do an example from your book. This is question 9. In the question, it is said that there is an electric field in a region of space, which is, its direction is constant, let's say the x direction, but its magnitude is position dependent. So we know that if you draw the electric field lines, at every point they will be horizontal. It need not be uniform. And inside here there is some volume. And then we are told that here at this surface, the electric field is, let's say, E0, the magnitude. And on the other side, the magnitude of the electric field is, let's call it E1. And just for simplicity, let's just assume that this is a cube where all the sides are length L. Well, the question in the book is slightly different, but the idea will be more or less the same. So if you want, you can just put in the numbers. So the question asks, what is the electric field inside this cube? Can we determine the electric charge inside the cube using this information only? Well, it is just the Gauss law. The mathematical expression for the Gauss law, let's just rewrite it, is Q over epsilon 0. If we can evaluate the integral of the electric field over this surface, then we can determine the charge. We don't know where the charge is. We don't know the charge distribution yet. But we can determine the total charge inside this cube, just using this much information. Now let me also show the other sides of the cube. Well, the cube has basically 6 sides. So this integral, I can divide it into 6 different parts. You see, if you remember what an integral is, you basically divide your area into various pieces, and in real life it's just infinitesimal pieces, but they don't need to be infinitesimal. You just sum the contributions. I can also divide my area, in this case at least, to 6 different pieces and calculate the contribution to the integral from each one of those sides separately and then sum them up. That would give me the total integral. So this will be equal to E dot dA over side, let me call 1. Let me just give them names. This is side 1. This is side 1 over here, side 2, side 3. The one on the back is side 4. This is side 2. The top I will call side 5. And this is, at the bottom, it is side 6. So it's just 1, 2, 3 on the back, this is the 4 on the top, it's the 5th, and on the bottom it's the 6th. So the total integral over all of the surface is just the sum from contributions from each one of the sides. Now let us look at side 2. This is the side facing you. What is the direction of dA on that side? It's pointing, you see the area vector is perpendicular to the surface. and it points from inside to outside. So if you define the inside as that smaller region, so the dA is pointing towards you. So this is the direction of dA. What is the direction of E? The electric field on that side 2 is in that direction. What is their scalar product? The scalar product is 0. We have two vectors that are perpendicular to each other. On that side, I don't know how the electric field changes. I'm not given that information. But I know that on that side, the electric field E is perpendicular to dA. So this scalar product at every point on that side is 0. So this integral itself is 0. What is the area element for, let's say, side 4? You see, this is side 2. The side 4 is on the opposite side. What is the direction of the area element for side 4? You see, this is our cube. This is side 2. This is side 4. What is the direction of the area element? Into the screen. It's always from inside to outside. So this is the dA vector. This is still the E vector. The scalar product is 0. Yes, your questions. Yes, yes. Well, side 4 is the one on the back. Now, I mean, when I look at you, I see that most of you is lost. So if you have questions, just ask me. I just caught one having a question over there. So side 4 is the other side. So here, 1, 2, 3, 4, 5, and 6. So just like the electric field is in that direction. Just like there's no contribution from here, there's also no contribution from this side because that dA is pointing upward. What is the dA for the top? Pointing up. The electric field is in that direction. The scalar product is 0. What is side 6? Again, it is 0. So there's no contribution from these sides. So this is 0, but also E dot dA from side 4 is 0. E dot dA from side 5 is 0. E dot dA from side 6 is also 0. These are all 0. The only surfaces that contribute to this integral will be this surface over here, side 1, and this surface over there, side 3. All the other ones will give 0. Because on all the other surfaces, the electric field is perpendicular to the area vector. So what remains? E dot dA is equal to E dot dA on side 1 plus E dot dA on side 3. So we just need to evaluate these two integrals. Now let's start from the first one, on side 1. On side 1, it is this side. This side. What is the direction of the area vector? In this direction. So let's see, E dot dA is the magnitude of the electric field on that surface, which is given to be a constant E0, multiplied by the area vector on that surface, the magnitude of the area vector on that surface, multiplied by cosine of the angle between the two. You see, on side 1, this is the dA vector. This is the electric field vector. So what's the angle between the two? Pi. So this is minus E0 dA. This is on side 1. On side 3, E dot dA okay, on side 3, the area vector is in that direction. Electric field vector is in that direction. So their scalar product is the product of the magnitude. Well, the magnitude of the electric field is given by E1 times the magnitude of the area vector, dA. Cosine of the angle between the two, it is 0. So this is just E1 times dA. So now we are back to these integrals. We have the on side 1, the integral of E dot dA, which we had just said that is equal to minus E0 times dA. This is this integral. And now we have on side 3, we have E dot dA, but that is E1 times dA. Now E0 and E1, they are just constants. I can take it out of the integral. If I take them out of the integral, this is just minus E0 dA on side 1 plus E1 times dA on side 2. Well, the sum of all the dA just gives me the total area, but it's a cube. The area of side 1 is just L cubed. The area of side 2 is also L squared, sorry. So that integral is minus E0 L squared plus E1 L squared, or E1 minus E0 times L squared. That is just this integral. And by Gauss's law, this should be equal to the enclosed charge divided by epsilon 0. This is the total charge inside the cube. I don't know how the electric field changes from this surface to that surface. I don't know what is the electric field on the sides. The only thing I know is that it is horizontal. And I know that it is constant on this surface and it's constant on the other surface. And from this information, I can determine what is the total charge inside. I don't know how the charge is distributed. Maybe most of them are on this side. Maybe they are more close to that surface. Maybe they are at the center. Maybe they are uniformly distributed. I don't know. But I know the total charge.
Is there any possibility for E0 and E1 which are equal?
It can be. Well, if they are equal, it just tells me that the enclosed charge is 0. It might be, for example, if we have two plates, two infinite plates, then we know that the electric field inside is uniform. In that case, well, E0 and E, if we just imagine such a cubical region within these two plates, the E0 and E1 will be equal, and they will be always horizontal, and the total charge inside is 0. Well, that is the system we started with. We said that there are only charges on the plates. There is no charge inside. Now let's look at some other problems. You see, we had calculated the electric field. Which cases did we study when we were discussing the electric field? we had the electric field of a point charge. And then we studied the electric field of an infinite wire. Let's see if we can use the Gauss law to determine the electric field of an infinite wire. So we have an infinite wire which has a linear charge density lambda. So if we take a length L, the total charge of that length will be L times lambda. So what can we say without solving the problem and just forgetting that we had already solved this problem before? What can we say by looking at the properties of the charge distribution only about the electric field? Yes, the first step is in applying the Gauss law is always to find something about the electric field. We first have to know something about the electric field, and then we can use the Gauss law. So what can you say about this charge distribution? What can we do to this charge distribution that it will not change? Okay, which means? So what can I do to this line that will not change the charge distribution? If you remember, in the case of the point charge, we said that if you rotate the charge distribution around that point, nothing should change. Can you imagine something similar here? When we put a mirror somewhere, okay, that is one thing. So if you just imagine a mirror over here, the image in the mirror and the real charge distribution, they are the same. So that is one property of the electric field or the electric field lines. So if you put a mirror and look at the images of the electric field line, it should look exactly the same as the real field lines. Okay, that is one property. What else? I am giving you a hint, by the way. If I rotate it, nothing changes. So that should be another property of the electric field lines created by this thing. If I rotate the whole system, the electric field lines should look identical. It shouldn't change. That's another property. Well, there's one more property of the electric field. There's another thing that I can do that will not change the charge distribution. Okay, I'm giving you another hint. Yes, if I push the wire in that direction, nothing will change. So we can use, to describe the electric field, we can use the cylindrical coordinates, rho, phi, and z. Now, if you look at the magnitude, well, z-axis, I will just take it to be this horizontal axis. So if I push the wire, nothing changes. By pushing the wire, I'm just changing the z-coordinates of various points. So nothing should change if I change the z-coordinate. It tells me that the magnitude of the electric field cannot depend on z. By rotating the wire, I'm changing the phi coordinate. If when I rotate, nothing should change, it just tells me that the magnitude of the electric field cannot depend on the phi coordinate. So the only thing that the magnitude of the electric field can depend is just the distance from the wire. So if I take this point, for that point, rho is this distance. So the magnitude can only, if at all, the magnitude can only depend on rho and on nothing else. What about the direction? What can you say about the electric field lines? Well, they should start from the wire. And they should go out, but they cannot have, they should make 90 degrees with the wire. If they go like this, the electric field lines, the mirror image will go the other way around. So that they should be straight. Still, there was one thing that we forgot. You see, in principle, if you just look at these properties, the electric field line can start from a point and go circling around. None of these properties that the electric field should not change under rotations around this axis. It shouldn't change under such a mirror. And it shouldn't change under translations. None of that tell us that the electric field lines cannot just go circles like this. But there is one more thing that we forgot. If you put a mirror like this, the charge distribution still doesn't change. In the image, it looks exactly the same. That is what prevents the electric field lines to go like a spiral. Because if it goes like a spiral in this sense, in the mirror image, it will go like a spiral on the other sense. So the mirror image of the field lines will look different. That is also not possible. Hence, the only possibility is that the electric field lines should just go radially outward. What is this direction in terms of our unit vectors? Well, okay, so in this diagram, I'm just drawing the 2 dimensions. Let me add the 3rd dimension. So these are my electric field lines. You see, if I would look from the side, you see, this is my wire. If I look at it from this side, I will just see a point as my charge distribution. And the electric field lines will have this shape. So do you remember this direction? Let's call it rho hat. It's the direction in which rho increases, and all the other things are constant. So now I know the electric field has to have this shape. The magnitude depends only on rho. It cannot depend on anything else. It cannot depend on phi. It cannot depend on z. And furthermore, it is only in the direction, it's in the direction where rho increases. So now we already know something about the electric field. So the next step would be, what is a surface over which we can evaluate this integral without knowing the magnitude of the electric field? So we should find some surface over which the electric field is the magnitude of the electric field is a constant. What is the surface over which the magnitude of the electric field is a constant? It's a cylinder. So we are looking at points whose distance from the wire is the same, whatever that constant is. Well, that is the definition of a cylinder. So this is my wire. So around it, I'm imagining a cylinder. Whose radius, let's just call it rho. But there is one problem, though. This cylinder is not closed. You see, when we are applying the Gauss law, we should evaluate the electric field over a surface that is closed. You see, if you just imagine the cylinder with open ends, it's not closed. So we have to somehow close it. Now, if we just take the surface for which rho is constant, then we cannot close it. So we have to find some other surfaces. Let's look for surfaces for which E dot dA is 0. Then they will not contribute anyway. So what is the direction of E, the electric field, away from the wire? So we should imagine some surfaces whose area vector is perpendicular to the electric field. What can they be? I mean, the electric field lines are, if this is my wire, the electric field lines are going in that direction, all around. What's the perpendicular direction to that? Well, up and down, they are perpendicular. So what is the surface whose area vector is up or down? You see, the area vector is perpendicular to the surface. So if this is my area vector, how is my surface? It's horizontal. Or it is perpendicular to my wire. You see, basically any plane that is perpendicular to my wire, that is crossing my wire at 90 degrees, will not contribute to E dot dA. But now that allows me to close my surface. I just imagine this flat cap here and a flat cap on the bottom. So this is my closed surface now. I close it here. This is also closed. It's just like a can. Now I have a closed surface. If I have a closed surface, I can use the Gauss law. So let's look at this integral first, E dot dA. Well, there are different surfaces here, just like in the example of the cube. I can divide my integral into various surfaces. The left side E dot dA plus E dot dA on the right side, over that surface side, plus E dot dA over the curved side. Well, to determine the left side and the right side, you see, on the left side, I don't know the magnitude of the electric field. On the left side, the electric field magnitude changes because left side contains different points at various distances from the center. So I cannot take out the magnitude from the integral. But it doesn't matter because E dot dA, since the electric field, I know that it is perpendicular to the area vector at every point on the left side, E dot dA is always 0. And similarly, on the right side, this is the direction of the dA vector. The E electric field vector is in one of these directions, depending on where you are. But they are always perpendicular. So it will always be 0, the contribution of this side. So this is 0. This is 0. The only thing remains is the E dot dA integral over the curved side. Now let me write the scalar product. The magnitude of the electric field at every point on the curved side. Remember, the magnitude depends only on the distance from the wire. Well, the definition of the cylinder is that all those points on that curved side is of same distance from the center. So it's just E rho. This is the magnitude of the electric field. And rho is a constant. E rho is a constant. I will take it out of the integral. Then the magnitude of the area, which is dA, times the angle between the two. The angle between the electric field and the area vector. Well, you see, when we are evaluating the integral, what we do is we just first take a patch. We imagine a very small patch on the surface. At that point, what is the direction of the electric field? It's upward, away from the wire. The A vector, which is perpendicular to that surface, is also in the same direction. They are both perpendicular to the surface. So the angle between the E and dA at that point is 0. If you imagine some other point, let's say over here, some other patch over here, the electric field at that point will be perpendicular to the surface. And the area vector will also be perpendicular to the surface. You see, at this point, this is the electric field, but this is also the direction of the dA vector. Again, the angle between the two is 0. Whichever point you imagine on the surface, the electric field will always be away from the wire and perpendicular to the surface, just like the dA vector at that point. So the scalar product E and dA is the product of their magnitude times cosine of the angle between the two, which is 0. Well, this is a constant. This is 1. This is 1. This is a constant. I can just take it out of the integral. But this is nothing but the total area. Remember, it's of the curved side only. Well, what is the area of that curved side? The area of the cylinder. Yes, I hear some 2 pi r's. Rho squared. Well, let me just give you one more number. This is L. The height of the cylinder is L. It's 2 pi rho times L. Well, you see, if you just imagine this cylinder, this is the cylinder. This is L. The radius is R. If you open it up, this is just a rectangle. And this side is the circumference of the cylinder, which is 2 pi rho. And the height is just L. So the area of this rectangle is the side area of my cylinder. So that's why it's 2 pi rho times L. And keep in mind that the area is always the product of 2 lengths, not 3. Okay, so now we evaluated the left-hand side of the Gauss law. And what Gauss law stated that if you evaluate this integral for an arbitrary surface, it should always be equal to the enclosed charge divided by epsilon 0. Now, what is the enclosed charge? Well, you see, this is my cylinder. Through the center, my wire is just going through the center. This has a total height L. So the length of the wire in my cylinder is just L. And since the charge density of the wire is lambda per unit length, the total charge will be just lambda times L. So we have E rho times 2 pi rho times L is just lambda over epsilon 0 times L. I can cancel the L's. E rho is equal to 1 over 2 pi epsilon 0 lambda over rho. Or if you write the electric field, not just the magnitude, lambda over rho in the rho direction. Here, whatever point you have, at a given point, if you want to calculate the electric field vector at a given point, you just multiply this constant by the charge density, it can be positive or negative, divide by the distance of that point from the wire. Rho is the distance of the point where you are evaluating the electric field from the wire. And it is in the direction pointing away from the wire, straight away.
I couldn't understand why E was a constant and A taken out.
Well, what we said, could you follow up to this point? So the electric field has a magnitude which depends only on the distance from the wire, and it is pointing away from the wire. So here, we said that from the left and the right planar parts, planar side, there is no contribution, there is only contribution from the curved side. And now we said, well, here we have a scalar product. Let's write the scalar product. What is the magnitude of my electric field? It's electric field at a distance rho, the magnitude at a distance rho, multiplied by the magnitude of the area element, which is dA, times the angle between the two. Well, they are both pointing. On the curved side, they are always pointing in the same direction, so the angle between the two is 0. Cosine theta is 1. So let's see. This is E rho. It depends on rho, but you see, we are evaluating this integral over a surface. I'm not evaluating that integral over all of my volume. I'm only on the curved surface. I take very small patches, and on those small patches, I evaluate the magnitude of the electric field, multiply it by the area of that patch, and sum them up. But all of those patches are at a distance rho from the wire. So as I go from patch to patch, rho doesn't change. Since as I go from patch to patch, rho doesn't change, for this integral, rho is a constant. I'm not changing rho in that integral. That is why I can take it out of my integral. And what remains is just the total area of the curved side. Other questions? You see, on one hand, we evaluated E dot dA over the closed surface that we had chosen. And we found that that integral is equal to E rho times 2 pi rho times L. On the other hand, what Gauss's law tells me that this result, this integral, whatever surface you have, should be equal to the total enclosed charge in the surface divided by epsilon 0. Now, any questions up to that point? Then we said, okay, so this is my wire, infinite wire. I am imagining this surface around it. This cylinder has a total height L. And keep in mind that there's a cap on the top and there's a cap on the bottom. Now this is the top cap. Now the length of the wire inside my cylinder is just the part between the top cap and the bottom cap. That is the total length of the wire inside my cylinder. So if you look at over here, from here to here, the wire is inside my surface. But that length is also L, because this plane and this plane, they are parallel to each other. So we follow that it is also L. Are you convinced? Yes. So, and in the question we are given that this wire has a linear uniform charge density, lambda. What does it mean? If you take any length of wire, let's say the total small l, you take a length of a wire L, you calculate the total charge of that length, let's call that QL. That ratio is always equal to lambda, independent of which length you take. So that also tells you that if you take a given length, the total charge in that given length is lambda times that length. So that is why we have over here a length L of my wire is inside my Gaussian surface. Per unit length, I have a charge lambda, so the total charge is lambda times L. Well, let's see. If my wire is not infinite, or let's say we also solve the problem of a ring. Which had a total charge Q. Can we use Gauss' law to solve this problem? My answer is no. Well, since I cannot really determine anything about the electric field beforehand, I cannot say anything. Well, I can determine the general shape, but I cannot really say anything about the magnitude of the electric field, or the direction, specifically the direction of the electric field. If we had a finite wire, some finite length, this time one problem I would have would be the electric field will be the magnitude will be a function of rho, the distance from the wire, but also of z. You see, the electric field at this point will be different than the electric field of this point, which will be different than the electric field over here. Also in this case, I cannot determine a Gaussian surface over which I can evaluate this E dot dA integral without knowing the electric field. Since I cannot evaluate that integral without knowing the electric field, there is no use. You see, but keep in mind, if I imagine such a Gaussian surface, exactly as before, with a radius r, height L. I just imagine, even for this surface, I just imagine such a Gaussian surface. For this surface, E dot dA over the closed surface will again be lambda times L over epsilon 0. This will not change. This is just the Gauss law. Gauss law is always correct. But I cannot use this equality to determine what the electric field is. It is still true, but not of much use. In this case, for example, on these surfaces, on the top and the bottom, on these flat surfaces, the electric field will not be parallel to the surface anymore. It will make some angle. So there will also be contribution from the sides. Over this curved surface, the magnitude will no longer be constant. The magnitude here will be different than the magnitude here and the magnitude there. So I cannot evaluate this integral. So basically useless. But nevertheless correct. So in that sense, Gauss's law, I mean, you can solve it if your problem has sufficient symmetries, like the infinite wire, or an infinite cylindrical charge distribution, or a spherical charge distribution, not necessarily point-like the example we did on Monday, then just in a couple of lines, without evaluating very complicated integrals, 2 or 3-dimensional integrals, you can determine the electric field. But if your problem doesn't have sufficient symmetries, like rotational symmetry, mirror symmetry, etc., it's basically useless to determine the electric field. Let's give a 10-minute break and then we will continue.